Good morning, Astronomy 1010. Nice to be back with you. Today we've got some important and difficult work to do. We have to learn Newton's laws of motion and his laws of gravity, and there's going to be quite a few formulas that we have to work with today to get us ready for our homework this afternoon. Have your Casio FX260 Solar ready. Let me get mine. We're definitely going to need this puppy today. Oop, we've got some autofocus issues. Let me open up that Logitech right now because it looks like we're going to need it. Okay. Let's start by talking about, well, at the end of our last class, we were discussing speed versus velocity, and we were just getting into acceleration. Let's just do a quick review verbally. Do you guys know the difference between speed and velocity? Maybe we could begin there. Jake, what do you think? You don't want to talk to me, Jake? You having some trouble with your audio? Frank, do you want to talk to me?
I'm just trying to figure, I know like, whoops, nope, that's,
Noah's
yeah,
playing video games or something. I don't know what Noah's doing. He's watching TV.
God damn it. That's my friend, there we go.
Okay, Enrique is hooking me up here. Velocity is a speed plus an acceleration. Thank you, Enrique. I really appreciate your contribution. All right, let's talk now about acceleration. And I started this last time, but you know, we'll start where we were last time. An acceleration, you will remember, is a change in velocity divided by a change in time. Although, if you really just, since everything takes time, nothing is truly instantaneous, you might say that an acceleration is just simply put a change in velocity, okay? And usually when we write down an acceleration, we write it using those delta symbols that I was showing you last time. Delta V over delta T. Usually, as you follow an acceleration, you watch it go from one velocity, right, at one time, v1, to some new velocity, v2. It's undergoing some kind of a change, and that change in velocity takes some change in time, and that's your acceleration. If you want to write it out, you can write it out as v2 minus v1 over t2 minus t1. Probably one of the most iconic accelerations that we could begin talking about is the acceleration that happens in our own gravitational field on Earth when we do something like drop a tennis ball and the magic of gravity pulls it down to Earth. Let's look at a little cartoon of that in our slideshow. I'm sharing my screen, and now I'm sharing this. And I want to go to slide 10, function F5, 10. Okay. In the figure that you see here, a cartoon man stands on the top of a building, like maybe CCRI, and he holds a tennis ball. Actually, I don't really like the way they drew this. It looks like he's throwing the ball. But if we're really going to just talk about the acceleration, the natural acceleration that Earth imparts to objects, we'd want to make sure that the observer is just kind of holding the ball, right? Hold on, I'm just trying to get my camera correct here. So we'll start by dangling the ball over the edge of the building, and we're not going to do anything crazy or violent. We're just going to hold it there, and we're going to simply release our fingers, and as if by magic, as soon as we release our fingers, the ball is pulled down to the ground. If we slow down and analyze what's going on, at the moment that we hold the ball over the edge, the ball is not moving, so its velocity should be 0. And that's the start of our experiment, t equals 0. And once we release our fingers, the ball begins to drop. And we discover, if we use some kind of a mechanism like a laser gate to measure its velocity, that after 1 second, the speed of the ball has increased to 10 meters per second. So we know that there's an acceleration because it went from not moving, v equals 0, to moving. At 1 second, the speed turns out to be 10 meters per second. And after 2 seconds, it's 20 meters per second. We could use these as 2 data points to calculate the local acceleration of Earth's gravity. And these are our 2 data points here. We could have used this one too, but we're going to use these for interest's sake, okay? And let's go ahead and let's try to do the computation here. So we have for our, so this is what's known as the local acceleration of Earth's gravity. This famous quantity was first investigated by none other than Galileo himself. And we're going to plug in our values and we're just going to kind of see what happens here. So the acceleration is, let's say our second velocity is 20 meters per second. Let's subtract that from our first velocity, which is 10 meters per second. And then the time 2 is 2 seconds minus 1 second. And I'm going to do the tough part here. I'm going to do the math because I know everybody's afraid of math. I'm going to do 20 minus 10. That will give me 10. And they have the same units, so it's 10 meters per second. 2 minus 1 gives me 2 seconds. And then, oops, sorry, 2 minus 1 gives me 1 second. What am I talking about there? Okay. Now, if I do 10 divided by 1, that's just 10. And what I want you guys is to tell me what my final units of acceleration are.
Would it still be meters per second?
It would not. And Ava, it would not be meters. Let's talk about Ava's answer for a second, because that's the one that I was expecting. You guys might be tempted to think that by dimensional analysis, seconds would cancel out. But you're misunderstanding what's going on there. You've got a situation where you have fractions within a fraction. And this tends to mess people up. So I want to do a little mini box on that over here. Let's say you've got the following. This is the situation that you've got going on here. You know, one of my fellow professors at CCRI has a little sticker or a little cartoon in their window, and it says, 3 out of 2 people are bad at fractions. And I think that's a pretty funny thing to say. Let's see if we can handle a situation where you have fractions within fractions, okay? So let's say you had, we'll make it symbolic. You had A divided by B, okay? And then you're going to divide that by C divided by D. This is a situation that actually comes up all the time because you've got fractions within a fraction. And the goal that we have here is to reduce this to a simplified fraction where we have some letters on the top and some letters on the bottom. Now, I don't want to drag this out too long. I don't know if you guys know how to do this. I have little nicknames for each of these letters, okay? I call A the top of the top fraction. I call B the bottom of the top fraction. I call C the top of the bottom fraction. And I call D the bottom of the bottom fraction. And that's just little cute ways to refer to them. Top of the top, bottom of the top, top of the bottom, bottom of the bottom. Now, the trick is to make sure you understand where they end up when you go into a simplified fraction. The top of the top stays on the top. That's easy. So A should end up here. The bottom of the top will drop down to the bottom. For instance, if you had 1/2 divided by 1/1, the 2 would end up on the bottom. C is the top of the bottom fraction. That stays on the bottom. The trickiest one is the bottom of the bottom fraction, letter D. The bottom of the bottom flips back up to the top. So your final reduced fraction is A times D over B times C. Please write all that nonsense down because that's going to be very helpful for you, not only in this class, but in many other classes as well. Okay, so Ava, if you can chat to me here, since you don't like to do the talking thing, which letter does M correspond to, Ava? Okay, talking to trolls is always a difficult thing to do. Let's talk to a real live human who's interfacing with, oh, okay, fine, Ava. Yes, the top of the top. It's letter, I asked you what letter, so it's letter A, right? So that should end up on the top. How about the first S up here? Which letter does that refer to? Good, B. So that should end up on the bottom. Now here's the real test, Ava. What about this S? Which letter does that correspond to? That's right. S here is the top of the bottom because if I wanted to, I could make that S divided by 1. And that means that I effectively have another S here. And meters per second means I end up with seconds squared in the denominator. And this is such an important quantity that we give it its own special letter. We give it the letter little g. And it has a value of 10 meters per second squared. Okay? Now, there's a couple of different things that I'm doing at once here. I'm telling you that the local acceleration of Earth's gravity, little g, has a value of roughly 10 meters per second squared. But I'm also telling you the units of acceleration, meters per second squared. Now let's tell you a little bit of history about this. The first person who measured little g was none other than our homeboy Galileo from our previous lecture. Galileo, of course, is the guy who built his own telescope and made a number of key observations supporting the heliocentric version of the solar system. Because Galileo had found much reason to mistrust philosophers like Aristotle, he questions Aristotle's wisdom when Aristotle claimed that if you dropped 2 stones to the ground, okay, he claimed that if he had a couple of different stones and one was more massive than the other and you dropped the massive stone, he claimed the massive stone would fall to the earth faster than the light stone because the massive stone would have more gravitas. In a way, that sounds like it might be true, but Aristotle wasn't the sort of person to actually investigate it by means of an artificer. He would not actually build this thing, but this is Galileo's own inclined plane. He had to slow the rate at which the ball fell to earth because he was going to be not able to time it if he dropped it vertically. So he constructed a ramp which would kind of slow the motion of the ball. And you can see here that he put these little tinkling bells on it. So as the sphere rolled down the ramp, he could time it with his ear and see if the rate was uniform or if it sped up. And it turns out, of course, that when he rolled spheres down this plane, they sped up and they increased their velocity with time. He also discovered that it wouldn't matter what type of sphere he used. He had spheres made of wood and spheres made of lead and spheres made of other types of metal. Whatever their density, whatever their mass, they basically all fell to Earth at the same acceleration, which is 10 meters per second squared. So a very cool science experiment done by Galileo. It's important for us to understand accelerations because in the next little module that we do, when we learn about Newton's laws, it turns out that accelerations are intimately connected to the concept of force. For instance, one of the wisdoms of Isaac Newton was to recognize that it's not just a change of speed that equals an acceleration, but a change in velocity. And forgive me for saying this again, but it bears repeating. If you are in a perfectly circular orbit, let's change our arrow color here. If you're in a perfectly circular orbit, your speed around the circle might stay constant, but your velocity is not constant. And that's because the direction keeps changing. Isaac Newton realized that if you change your direction, that requires an acceleration because something has to, because as you're about to learn, an object in motion tends to stay in motion, all right? Excuse me there. Now it's time for us to discuss the great works of Sir Isaac Newton, who wrote this famous book, The Principia of Mathematics by Isaac Newton. It's a work not only of physics, but a work of philosophy because of the good judgment and wisdom it contains. This is now a classic of Western literature. It's hard to emphasize just how important this book is. This book had clarity of thought, and for the first time, it gave people good judgment about how motion should work. And remember that Isaac Newton also gave us concepts like the force, which we had never really articulated properly before. So it's time for you guys to learn Newton's 3 laws of motion. Okay. The first law of motion is the law of inertia. And that law of motion says an object in motion tends to stay in motion unless acted upon by an outside force. So Newton is claiming that objects in motion will maintain a constant motion unless a force changes their motion. This is another way of saying forces are the things that change the motion of objects. This was also a direct refutation to one of Aristotle's laws of physics. In Aristotle's laws of physics, he claimed that if you were to take a stone and you were to slide a stone along the ground, it would eventually come to rest. That stone, if you pushed it along the ground and let it go, the stone would actually come to rest by its own volition. And Aristotle implied that the natural state of being was for things to be at rest. He actually kind of had confused sideways motions and the downward motion due to gravity. He claimed that the reason a stone eventually stops rolling is because it desires to stick to the center of Earth because of gravitas. So he was saying gravity forces things to stop. And that kind of sounds good, but the problem is it's not good. It's not good because Newton could see that there were other forces and other things interacting with the stone. Not only did it have gravity pulling it down, but when you roll a stone along the ground, it has friction between the surface of the stone and the resistance. What you call resistance, Enrique, I would call friction. The force of friction pushing on the stone is a side-to-side force. Newton was able to see that if you could bring this stone into outer space where it was free of external media, and you could just give that stone one little push, one little poke or tap, that stone would just start to travel in a straight line and it would never stop. In other words, Newton had basically figured out the principle behind the video game of asteroids, okay? So basically, Newton was the first person to figure out how the video game asteroids work. He knew that if you have to shoot these asteroids in the video game, you guys are probably too young to have played asteroids, but you know, go to a pizza parlor, go wherever they have old school video games, and play asteroids, and you will learn about Newton's law of inertia. As you rotate the ship around to shoot the asteroids, sometimes the asteroids get a little close to you, and if you fire the thrusters, the ship will start to move across the screen, and it will not stop moving unless you rotate it 180 degrees and fire some retro rockets. Of course, Newton didn't have asteroids at his local pizza parlor, did he? He had to think of this the first time. He didn't get to grow up watching science fiction movies like we did. So he had to figure out how would objects move in space if they were not subjected to frictional forces. Now, so far he's told us that force is something that changes motion, but he hasn't told us what the force is, and that's the job of the next law. Hey, Brooke, I'm digging your world map background. That's pretty cool. I want that.
Thanks, Amazon.
Oh, is it a big poster?
It's like a tapestry. It's like a sheet thing.
Wow, that's pretty dope. If you ever think about it, send me the link to that, because I'm kind of a map nerd. I don't know if you noticed, but I got a bunch of globes floating around my house, so I'm kind of into globes and maps and things. Anyways, I was just admiring. That's a good backdrop. Okay. Let's talk about the second law of motion. The second law of motion is the definition of force, and it could be one of the most iconic formulas in all of physics, okay? It's the definition of a force. It's a math equation, a kind of very important math equation, that says force is equal to mass times acceleration, okay? So that's force equals mass times acceleration. You guys can think of a force in a loosey-goosey sense is kind of like a push or a pull. Anything that gives a push or gives a pull is a force. But what's cool about this is this properly defines how we should calculate or compute a force. So now we can do things. For instance, check this puppy out here, right? This is a 1 kilogram reference mass. I know what the mass is because it says it right up here on the top, okay? Now, if I hold this on my finger, gravity is exerting a force on this kilogram mass, and it's trying to rip it out of my finger and pull it to the ground. And I can feel that force pressing down on my finger, and quite frankly, it kind of hurts a little bit, okay? Now, we can calculate the magnitude of this force because we know all the quantities involved. We know the mass is 1 kilogram. What's the acceleration, students? Please think quickly because my finger's hurting.
G.
Little g, 10 meters per second, right? So let's go ahead and do that. And by doing that, we're going to teach ourselves the units of force. Okay, so let me erase the first law up here. And let's imagine we have a 1 kilogram mass suspended off the finger of a professor. Okay, so there's my finger. And the mass is 1 kilogram. And little g is 10 meters per second squared. All right. We could calculate the force. Let's check out our units in red here as 1 kilogram times 10 meters per second squared. And that force would then equal 10. Class, help me out. What are the units here if you smush them all together? Make a common fraction from those units.
Isn't it kilograms times meter divided by 2 squared?
seconds squared, right?
Second scale, sorry.
2 squared is 4. Okay, yeah.
Yeah.
Well, I knew what you were saying. That's correct, Bella. Very nice. So it's kilograms times meters per second squared. Essentially, if units tell you what's going on, those are your units of force. It's more elegant sometimes to say kilogram meters per second squared. Now, I know what a kilogram and I know what a meter is. I know what a second is. But a kilogram meter per second squared is like kind of confusing. It's kind of abstract. So a better strategy is to hide your confusion by inventing a new name for this unit. Henceforth, this unit will be known as 10 newtons of force, or 10 capital N. And because newtons are kilogram meters per second squared, that means newtons are an Mks unit of force. So the Mks units for force, 1 Newton is defined as 1 kilogram meter per second squared. Let's not forget that. That's important. Do you guys know what the imperial unit of force is? Come on.
Is it pounds?
That's right, Noah. Pound. A pound is defined as 1 slug foot per second squared, I think, because we use slugs feet in seconds. Okay, let's talk about Newton's third law, and then I want to move on. The third law of motion of Newton is kind of like an iconic statement. It says, for every reaction, there is an equal but opposite reaction. Keep in mind that for a person of Isaac Newton's day, action was a way of saying force. For every action, there is an equal but opposite reaction. And the reaction is a counterforce. The idea is that forces can only exist if they happen between pairs of bodies, or at least if they involve 2 directions. Let me just show you an example of that here. Here are 2 examples of the third law of motion. If your finger presses against a wall, you're exerting a force on the wall. But usually when you press on a wall, your hand doesn't move. The only conclusion Newton can reach is that the wall must be pressing back on your finger with an equal but opposite force to prevent you from moving. What about things that do move, you say? Well, that could be like a rocket. When you thrust a rocket forward, you have to expel gases backwards. And as you push the gas backwards, you exert a force to the right. A counterforce must result that pushes you to the left, okay? And if you've ever sort of tried to fight your little brother while on inner tubes in a pool or a lake, then you know all about this, right? You know when you push your brother in the little tube that he's gonna go one direction, you're gonna go the other direction. These are things that should make sense to you. However, they are not always obvious, and sometimes they can have surprising results. Now that we know Newton's laws of motion, we now have good judgment about how forces work, what a force is. A force is some kind of kilogram meter per second squared, and we have some rules for how forces should work. But Newton did not stop there. After coming up with his laws of motion, he then set out to try to understand gravity. And there's some funny stories about this. In Isaac Newton's day, Newton was going through a situation that's kind of quite similar. Oh, Shaughn played asteroids, cool. Newton actually went through a situation that was kind of similar to the situation that we have today with the COVID-19 pandemic. During Isaac Newton's time in college, Europe was being ravaged by the bubonic plague, and nobody knew what was causing the plague, except a lot of people were dying, and people were freaked out, and they had to leave college. Let's type in Woolsthorpe into Google here. Woolsthorpe Manor is the name of Isaac Newton's ancestral home. And believe it or not, that house still stands today. Here's a picture of it with an apple tree in the front yard. I think the apple tree is here, actually. That doesn't look like an apple tree. So Isaac Newton had to leave, I think, Trinity College because the bubonic plague was killing lots of humans, and they thought that perhaps it was because of bad air in the city of London. So he had to do what a lot of you guys are doing today. He went home to live with his parents, and he went upstairs in this attic, and he brought his textbooks with him. And his textbooks included works by Galileo and Tycho Brahe and Kepler, all the famous people that we've studied so far in our History of Astronomy lecture. And he writes in his journal that one day he was occasioned by the fall of an apple. He watched an apple drop to the ground, and he said it made a big impression on him because he realized that the same force that's pulling the apple to the ground had to be related to how the moon keeps its circular orbit. He started to reason that the moon in a circular orbit should want to travel in a straight line unless acted upon by an outside force. But what happens is the velocity is changing, and the velocity keeps pointing along this circle. It made him realize that there must be an acceleration at work, and the only thing he could conclude was that the acceleration was actually down towards the center of the Earth. So that the resulting motion of the moon would be a combination of its sideways motion, its downward pull to Earth, and that's how it would end up traveling along the circle. In other words, the fall of the apple and the fall of the moon were somehow related to each other. Now, the actual story of how he came up with the formula for the law of gravitation is a little bit more involved, so you're going to have to forgive me if I skip that one. But our goal today is to kind of learn what he came up with and learn how to use this formula. Let me introduce to you the formula for Newton's law of gravitation. And the setup is that we have two arbitrary masses, M1 and M2. They literally could be anything with mass. They could be two bowling balls, but we'll pretend for the time being that one is the mass of the Earth and the other is the mass of the moon. And the force between them is proportional to the product of their masses and inversely proportional to the square of their distance. That's how Newton wrote it. Let's go ahead and put that on the board because that's going to take some explaining.
I don't have the other part of number 3.
Oh. I'm sorry. Andrew?
Yes.
The other part of number 3 is for every action, there is an equal but opposite reaction. So that was slide 45. And here's slide 24. While I erase, just copy it down right from the slide there, right at the top. That's all I wrote down. Sorry about that, buddy. Okay, so introducing the law of gravitation.
I got it.
You got it? All right. Let's go ahead and let's draw the setup the same way that Newton had it in the Principia, okay? So I have two masses, M1 and M2, and they are separated by a center-to-center distance, little d, all right? Now, the way that Newton wrote his law of gravitation is kind of interesting. He wrote it in the following form. The force of gravity is proportional to the product of the two masses and inversely proportional to the square of the two masses. Where I've used a new operator, this little Jesus fish thing is called the proportional to operator. It's a powerful operator that can allow you, it's different than an equal sign. You don't use proportional to find the magnitude of the force, how many newtons. You use it to figure out if I vary any of these quantities, how will the force change? Let me give you an example because this is going to show up in our homework today. So a simple example would be something like this. Suppose I double the distance between two masses. If I ask the question, how would the force vary? I would answer it in the following way. I'm going to ignore masses because they're not changing, they stay fixed. And I would simply write that the force is inversely proportional to the square of the distance. Notice that the d stays on the bottom where it belongs, and it keeps the little square with it because that's important. Now, if I double the distance, I'm changing the distance by a factor of 2. I haven't specified what the original distance was. It could be 2 meters, it could be 2 million meters. Who gives a crap? All that matters is that the distance has doubled. And here's how I use that proportionality. If the distance varies by a factor of 2, as long as I'm using proportional, the proportional operator, I can just plug in the factor of 2. So 1 over 2 squared. At this point, I can turn it into an equal sign because I just want to evaluate that fraction. Now, the new force is 1/4 the old force. Or in other words, that's the same as saying 4 times weaker. If I double the distance between Earth and the moon, the gravity would drop by a factor of 4. Proportionality symbols might seem silly at first, but they are powerful tools that can help a thinking person quickly evaluate how a formula works. I can't even begin to explain to you how many cool things that you can do with the proportional 2 operator. Of course, students, that's not always enough. Sometimes we actually want to calculate the force of gravity. And Newton actually never figured out how to do that. And the reason why sort of has to do with units. Class, if we're going to use MKS units, then remind me, what are my MKS units of mass again?
It's kilograms, right?
Thank you. What are my MKS units of distance?
Meters.
And what are my MKS units of force?
Slugs.
False. That is an imperial unit of mass.
Is it meters per second squared?
No, that's a unit of acceleration.
Oh, never.
Newtons.
Newtons. If you had said kilogram meters per second squared, you would have been right. But you forgot the kilograms. Okay. Newtons is a simpler way to say it. Now, did humans invent gravity, students? Who invented gravity? I guess that was Odin, right? Or Vishnu, or whoever your local deity is. So Jesus waved his... The universe invented gravity. The universe herself. But do you know who invented the kilogram? Man invented the kilogram. Some human being decided that this should be a reference unit of mass. That if we're going to talk about stuff, this should be the reference by which all stuff is measured. And by the way, humans also invented the meter right here. It's about the size of a yard, okay? Humans decided this should be a standard unit of length. And that means that humans also invented the Newton. But humans didn't invent gravity. If you want to turn this into an equal sign, you have to go out to nature and you have to ask nature, hey, nature, just how hard do you plan on tugging between two objects? And probably the simplest way to do it would be to say, hey, nature, if I had 2 kilogram masses and they were separated by 1 meter from each other, how strong would you tug on that? We have to ask nature how gravity works. We don't get to impose that. Newton couldn't really figure out how to do that. The person who did came later, and that person's name was Henry Cavendish. And Henry Cavendish did this famous experiment, Cavendish experiment, where he found a way to measure the strength of gravity. And he did something pretty wild that you wouldn't think would work. He took 2 large spheres. They were probably like 2 bowling balls or something. I'm trying to find a clean, easy to look at picture here. Maybe this one. So he took these massive spheres made of lead. They were kind of like bowling ball sized spheres. And he held the really massive ones, the purple ones, fixed in place. And he suspended some slightly smaller ones, the green ones, on a very thin rod suspended by a very thin wire that could rotate. This is what's known in physics as a torsional pendulum, because you apply torque to the spheres. And believe it or not, you wouldn't think this would work, but he could actually measure a tiny deflection by gravity, and the 2 spheres together actually pulled a tiny bit on the little spheres, and they got this wire to twist. And then he was able to measure the deflection very precisely because he could shine a beam of light or a laser on the mirror, and as the mirror twisted, you'd measure this angle by which it rotated. In other words, he performed this clever experiment where he actually measured nature's pull of gravity. By doing that, he was able to turn this into an equal sign. Now, Andrew, hold on to your socks because I'm going to do some erasing here. Cavendish was then able to rewrite the formula in this way. The force of gravity is equal to big G times the product of the 2 masses divided by the distance between them squared. This is Newton's law of gravity, although it should be called Newton with help from Cavendish's law of gravity, where if I have introduced big G, known as the universal gravitational constant, you can think of the universal gravitational constant as an index of the strength of gravity. And according to Cavendish, it has the following value. Big G is equal to approximately 7 times 10 to the minus 11. The units are meters cubed per kilogram per second squared. All right. The next order of business is for us to try this formula. Adam, Frank, Andrew are still writing. Andrew, let me know when you're done copying, okay?
I'm done.
Is everyone else cool? Because I need to erase this.
Yeah, I'm all
Give me
set.
1 second, sorry.
That's fine. Take your time. I'll sip some tea. This is important. It gives me a chance to drink tea from my Chengdu taste mug. We're going to need some caffeine for this next bit, trust me. So class, while they're finishing up here, here's the Earth, here's the moon. What do you think is stronger? The force of gravity between the Earth and the moon, or the force of gravity between the Earth and the sun? Take a guess.
Would it be the Earth and the sun?
What makes you say that?
Because of the mass of the sun is greater than the mass of the Earth.
That's true. Who said that?
That was me, Frank.
Oh, hi, Frank. Sorry, you're hidden from my display right now.
I was gonna say I got my video on.
Yeah, I can only, when I'm in speaker mode, I can only see a few people at a time. So there you are, Frank. Okay, Frank, so what causes tides then?
Oh, well, the moon causes tides because of I remember learning this last year in your class.
It's tricksy. It takes a couple of times to really drive it home. Okay, look, let's do a computation. That's what the class needs right now. We're going to calculate the gravity between Earth and moon. Then we're going to calculate the gravity between Earth and sun. Let's make sure Frank knows what he's talking about. And then we'll talk about tides, okay? Those are all going to be in our homework today. So get your calculators out and hang on to your socks. Everyone's got this, right? Because I'm erasing it. So here's your question. Find the force of gravity between Earth and the moon. We're going to need some data to do this. I'm going to help you out. The mass of the Earth is 6 times 10 to the 24. Let's use blue for units here. 6 times 10 to the 24 kilograms. Students, I don't want you to freak out, but that little circle with a cross in it, that is the astrological symbol for the Earth, all right? Sometimes we have little symbols for Earth and moon. The mass of the moon also has a symbol. It's like a little crescent, but I kind of suck at drawing a little crescent. So usually I just, see, that's kind of hard to draw. So usually what I just do is write mass subscript m for the mass of the moon. That's 7 times 10 to the 22 kilograms. And if you ask Neil Armstrong, the distance to the moon is 384,000 kilometers. Okay, let's go about calculating our law of gravitation. So let's look back at the law of gravity here in our slideshow. Oh, I can't remember what number it was, so I'll just...
I didn't get the distance. What is that?
Sure. 384,000 kilometers.
All right, I got it.
All right. So, Andrew, what units are we supposed to use for mass here?
What units are we supposed to use? Okay. Mass. Kilograms.
What units are we supposed to use for distance?
Meters.
What units were we given for distance?
N.
What? No. Look, this is our distance. What units were we given?
Oh, kilometers.
That's a bit of a problem, isn't it? You know where I'm going with this, don't you, Andrew?
No, not really.
Andrew, I'm going to need you to convert kilometers to meters using dimensional analysis. That's the only way I can do this problem.
Oh, all right. So
Could you
it's
help
the
me do
problem.
that?
So
The first
yeah,
step of
so
dimensional
it's-
analysis is to write your number down with its units, and I've done that. What's the second step?
So you got to put it into like a fraction bar.
Okay. What's the third step?
Oh, you got to write down your units.
Good. So tell me what units to put, top and bottom.
So it'd be.
Don't look it up. You don't need to look it up. You just need to look at my board here. That's all you need to do.
All right.
What are you trying to get rid of, and what are you trying to convert it into?
Oh, I'm trying to get rid of the Earth, the moon.
Wait, you're not trying to get rid
So
of the,
you would write.
You're not trying to get rid of the moon. You don't want to get rid of the moon.
Oh.
You're trying to convert kilometers into what units?
Kilometers into kilograms.
No. You can't convert kilometers into kilograms. You said yourself just a moment ago, what are the units that we need for distance?
Oh, meters.
Okay. Okay, so what units should go on the bottom and what units should go on the top? Your first job is to kill the kilometers. How do you kill kilometers?
Oh, with the meters. With the.
No. You're missing something here, buddy. The way you kill off units is you have one unit on the top and you have that same unit on the bottom, and they cancel out, right?
Oh, yeah. So kilograms would have to be down here.
No, kilograms are mass. We're working with length here. But keep going. Not kilograms, but kilo what?
Kilometers.
Where would they go?
At the top?
Does that cancel them out?
Oh, no, the bottom.
Yeah,
Bottom.
they've got to cancel out. That's your motivation. What am I going to put on the top?
Kilo.
Yes, Ava.
Grams? No, wait.
No, you just have to remember,
Yeah,
what were you trying to convert into? You said it twice.
Oh, meters.
That's right. Okay, now step 4. You need a conversion between meters and kilometers. What's your conversion, Andrew?
My conversion is. Oh, we're just going to write down the 6 times.
No.
10.
No, you're looking for how many kilometers is equal to how many meters? Question mark kilometers equals question mark meters.
Question mark.
You can find it like in your notes or in one of those notes that I handed out. Let's see here.
Oh, I found it. So it'd be G equals
No.
a number.
Nope, that's
M
a
over
different thing.
S.
These are your lecture notes here. Now, I gave them to you also, but it's going to take you a while to fish through your notebook. Did I give them here? I thought I did.
Yeah, it was with the angular size. Earth's orbit.
Yeah, I know they are in your notes.
Scroll down.
Is it in those notes?
Yeah, it was just above the angular size.
Oh, bloody hell. Well, I lost them now. They're hidden from me now. All right, someone help him.
1 kilometer equals 1,000 meters.
You better write this down in really, really big font, Andrew, okay? Write this down.
All right.
You know this.
Kilo equals 1,000.
Right. Could you please write that down in your notes and put a box around it? Where are you, Andrew? There you are. Okay, Andrew, you're not done yet. One of these numbers has to go on top and one of them has to go on bottom. Can you help me figure that out?
All right, so the meters goes on top, the 1,000 meters.
Correct. And then what goes on the bottom?
Oh, the 1 kilometer.
Yeah. Okay. Now, let's see if we can do this in your head. How many zeros do you have there?
I have 3 zeros.
And how many zeros do you have there?
3 zeros.
For a total of how many zeros?
6 zeros.
So I can write this as 384 times 10 to the,
Times 10 to the 6th power.
and that's meters. And that's the units we need for our law of gravity. And now we can set up the equation and compute the force of gravity between Earth and the moon. Let's go ahead and do this. Hang on to your hats. The force of gravity between Earth and the moon is, first we have to multiply by big G, 7 times 10 to the minus 11 meters cubed per kilogram per second squared, times the mass of the Earth, 6 times 10 to the 24 kilograms, times the mass of the moon, 7 times 10 to the 22 kilograms, all divided by the distance, 384 million meters. And I want you to watch how I write this, parentheses squared. The first time you punch this into your calculator, it's gonna suck a little bit, okay? But it's actually not that hard. You just need to train yourself. Let's make sure everyone's got that copied down, and then we're gonna punch together.
Brendan,
Yeah,
is that 7 times 10 to the negative 11? Is that always, is that just like a constant?
yeah.
Or,
They call it the universal gravitational constant because as far as we know and believe, Noah, that number is the same wherever you go throughout the entire universe.
okay,
They
so we're
call
going to
it-
have to just remember that one?
Well, I guess if you were doing this like without a safety net, you'd have to remember it. But to make your mind at ease, Noah, during the exam, which is really the only time you're going to have to kind of tightrope walk, I will provide you with a formula sheet, which not only will have all the formulas that we've discussed written down on it, but I will also include the constants of nature with their units. So on the formula sheet, you'll see, in fact, just so you can get a sense of what that would look like, Noah, somewhere.
Brendan, I have the one from last semester. that I can
Yeah,
show.
in theory I should, yeah, okay, it's probably not going to change too much.
It looks something like this, guys.
Yeah, it is. Thanks.
Here, I've got it right here. It took me a second. So Noah, if you can see my screen here, you'll see that like, not only I provide you with the law of gravitation, but you'll see that I have the gravitational constant with units. Now you might think, Noah, oh, that shit's gonna be easy. Now my job's all done. But I would warn you to be careful because even though you have the formulas and even though you have the constants, I don't always tell you what the units are here, and it can just still be really confusing. So don't get too cocky. But you'll notice that, like the way Andrew forgot the number of meters in a kilometer, I'll also have that there. So when you said, am I going to have to remember this? It's not that you're going to have to remember this number specifically, but you will have to remember the idea that that number needs to be plugged in and so forth. You know what I mean? You're still going to have to remember things. The good news is, Noah, the more we practice doing it, the more you will accidentally remember it. That's my hope, okay?
Yep.
We'll see. All right. Guys, should we try to punch this in together here? You ready? Now follow along with me, and then I want to see everyone's number. So first we'll do big G. So let's do 7 exp negative key 11 times 6 exp 24 times 7 exp 22 divided by 384 exp 6. Now we're going to have to square that. So go up here and hit your x squared key, squared, and then hit equals. Everyone hold your calculator up to the screen. I want to see what you got. Adam, I like it. Joel, I like it. Rory, like it. Kelly, like it. Bella, I like it. Keep holding it up there. Andrew, I like it. Okay, so you guys all seem like you know what you're doing. I've seen. All right, Ava's got it. Henry, you got it? Yes, okay. All right, so that's a happy moment. Hey, Henry, how should we round that? What do you think, Henry?
2.0 times 10 to 20.
What do I write down on my paper, Henry?
2 times 10 to 20.
Yeah, could you say it louder?
2 times 10 to the 20th.
And what are the units, Henry?
Newton.
Very good. All of those units cancel out. Meters squared cancel with meters cubed and leaves you 1 meter. One of the kilograms cancel out, so you have kilogram meters per second squared is a Newton. That's the force of gravity between Earth and the moon. 2 times 10 to the 20 newtons. Okay, I want to do this once more for the Earth and the sun, and this time I want you guys to punch it without my help, okay? Let's go back up to the top. Question number 2. Find the force of gravity between Earth and the sun. The mass of the Earth will stay the same, but now the mass of the sun is 2 times 10 to the 30 kilograms. Where I have used the astrological symbol for the sun, which is a circle with a dot in it. Class, what is the distance between Earth and the sun? How many kilometers is that? Or what do we call the distance between Earth and the sun?
An astronomical unit?
Yes, Rory. Do you remember how many kilometers it is?
I can tell you in 1 second when we find it.
That sounds good to me.
150 million kilometers.
Okay, Rory, since you're such a badass, can you tell me how many meters that is?
That would be 150 billion.
Very good. Let's see what he did, class. He knows that just like before, he's going to multiply by 1,000 meters per kilometer. Add 3 zeros to 6 and you get 9. Bada bing, bada bang, bada boom. Okay? Now, let's plug it into our equation. The force of gravity between the sun and Earth will be all this stuff, but here I'm going to change the second mass to be the mass of the sun. 2 times 10 to the 30. And I'm going to change my distance to be 150 billion meters. Now, I'm probably going a little faster because I didn't rewrite everything. Let me just give you a moment to catch up while I get a sip of iced tea, okay? I'm fiercely thirsty for iced tea. So this was the Earth and Moon. I want you to copy down and I want you to plug it into your calculator. And when I come back with my iced tea, I want to see the answer. Okay. See if you can punch it without my help.
Right in.
Yeah. That's good, Joel. Joel's got it. I want to see some others. Basically, my question is, oh, hold that up, Rory. Hold that up, baby. Yes, Brooke. Yes, Rory. Yes, Henry. Okay, you guys are making me proud. I didn't know if that was going to be hard for you, but Bella, I like it. Let's see if we can get Adam. Yin, I'm just seeing like the top of your bun there. I don't know what's going on. Yin, hold up your calculator when you get something for me. Jake, how you doing? Oh, you've got problems talking. Jake, something went wrong, buddy. Punch it again. I think you forgot to square your distance and then hit equals. Adam, what's going on? Are you struggling, Adam? A little bit? Okay. You want to do that together? Should we do it? All right. That's fine. It takes, some of these guys are veterans, so the veterans are going to find it a little easier. They've taken my Astronomy 1020 course. Let's punch it again, okay? I'm going to adjust my focus so I can get my calculator real close. I don't know if that helps you guys anymore, but let's try it for the hell of it. So I think if I go to about 33 or so, I can get my calculator nice and close to the screen. Okay, clear out. First, we're going to put in big G. So watch. 7 exp negative 11. Now we're going to multiply by the mass of Earth times 6 exp 24. Now we're going to multiply by the mass of the Sun times 2 exp 30. Now we're going to divide by the distance and square it. So we're dividing by 150 exp9 for billion. Now we got to square that. So go up here and hit square. But then we have to equals to complete the equation. Did you get that, Adam? Yes, sir. Who else? Frank's got it. How about, let me see the rest of you here. Yin? Yin, what's going on with your bun there? Okay, that looks good. All right. It sounds like you guys have it now. That's good. You're going to have to practice this to get it good, okay? Yes, Ava. I have no problems doing it again. Now, I'm going to move a little quicker this time, Ava, so hang on to your socks, okay? Okay. 7 exp negative 11 times 6 exp 24 times 2 exp 30 divided by 150 exp9 square key equal key. Okay, great. I'm glad it worked for you. No shame in doing it a couple of times, guys. Hey, Cam, I like the looks of that. That's good. Okay. So, how do we round it then? Hey, Adam, how should I round this?
Round it to.
Be bold, just like we did before.
So you would do F equals. My calculator's dying on. So you do F equals 3 times.
Well, hold on, what's the number after 3? Is $3.70 closer to $3 or to $4?
$4.
So,
So-
try again.
So it'd be 4 times
10.
10 to the 22.
And the units?
Be newtons.
Correct. Okay, I love it. So class, was Frank correct? Was the Sun-Earth gravity greater than the Earth-Moon gravity? Was Frank right?
Yes.
What do we? Yes, Frank was right. Okay, here's the big question. How many times greater is the sun's gravity than the moon's? To compare it, we will divide the force of the sun-Earth divided by the force of the moon to Earth gravity. And we will have 4 times 10 to the 22 newtons over 2 times 10 to the 20 newtons. Okay, Brooke, 4 divided by 2. 2. 22 minus 20. 2. What are the units, Brooke?
Still newtons, right? Yeah.
False.
No?
Newtons cancel.
Oh, how many times greater?
Yeah.
Is it
What is 2 times 10 to the 2? What's that number?
200.
200.
so 200%?
Not percent. Not percent. 200 times greater. Brooke, if you bake 5 cookies and I bake 10 cookies, and someone asks us to compare our cookies, 10 cookies divided by 5 cookies is the number 2. The meaning of the 2 is not 2% more cookies. The meaning of the 2 is not 2 cookies. The meaning is I have 2 times more cookies than you. Okay? If I divide the sun-Earth gravity by the moon-Earth gravity and I get 200, that means the sun is tugging on Earth 200 times more than the moon is tugging on Earth. Okay? I've got more to say about that, and I've got some things to say about tides. But I only have 10 minutes or even less than 10 minutes left. And keep in mind, today's homework, you guys are doing a homework today, right? It's going to be kind of hard. Like the stuff that you just did is the easy stuff. I'm going to take my last 10 minutes and use it as best I can by teaching you one more formula that we need several times in today's homework. So I'll have to fill in some of the details and the gaps later, but I think it's more important for us to do a module on Newton's version of Kepler's third law. Okay, I need to erase. Is that okay? Can I erase? All right. Newton combined his laws of motion. That's fine, Cam. We will be taking a break before homework, but we got one more module to do. I'd like to introduce something called Newton's version of Kepler's third law. It's kind of a big deal in our astronomy class. This formula is an improvement to Kepler's third law. Kepler's third law is something you're supposed to know. Can you guys remind me what Kepler's third law goes like? How about you, Jake? I bet you're the kind of fellow who would know about Kepler's third law. Or would I be mistaken in that? Oh, yeah?
It's the harmonic law.
Yep. And how does it go?
Formula is p squared equals a cubed.
Now, the two things you need to know in addition to that, thank you, Ava. What are the units and what does it mean? Let's start with the units. That's probably more important. What is P to be measured in?
Years.
Good. And what about A?
AU, astronomical units.
And what is the P represent?
The period of the planet.
Yes. How about A?
The distance to the planet.
Yeah. Now here's where I'm going to tell you something new. And thank you, Ava. This formula only works, you'll remember, if you were paying close attention to my lecture on Monday, you'll remember that Galileo lost respect for Kepler because Kepler asked him to try p squared equals a cubed for the moons of Jupiter, and it didn't work. That's because this only works for orbits around the sun. In other words, this will work for planetary orbits. It will also work for both comets and for asteroids, because both comets and asteroids orbit the sun. But it will not work for moons. And although this won't be much of an issue in our solar system course, it won't work for binary stars either. We don't really cover binary stars in Astronomy 1010, but I'm telling you that for completeness. Newton discovered that he could make a version that would work all the time for any two orbits because he knew the law of gravity and he plugged the law of gravity into this equation. He came out with a juicier version of this formula. It goes like this. P squared is equal to 4 times pi squared times a cubed divided by big G times the sum, not the product, but the sum of the two masses in parentheses. This formula requires new units. The P will be measured in units of seconds. It's an MKS formula. The A must be measured in units of meters. And the masses, of course, will be measured in kilograms. In other words, this formula requires MKS units. Notice that p squared equals a cubed does not use MKS units. AUs and years are not MKS. They're whatever units. Okay, this formula works for any two masses that are in orbit around each other. In other words, the picture is mass M1 and mass M2. Keep in mind that in the law of gravity, the distance between them was d, but now the distance between them is a for semi-major axis. And the mass 2 is kind of orbiting around the mass 1. You could think of this as like the moon and the Earth, except now the distance is called a. Watch out for that.
Is the one on the right, that's Newton, right?
Yeah, that's why it's, by the way, because this is such an
I could see
important
it.
formula, we sometimes in my class, I nickname this formula NK3. I like to call it NK3 because it's easier than saying Newton's version of Kepler's third law. Normally, if I were to introduce a big old badass formula like this, I would immediately try to have us do a sample problem so you guys could practice it. But guess what? We're about to do our homework, and you're going to be practicing it not once, not twice, but at least 4 or 5 times. So I think we could probably just save the sample until the homework session. Does that sound okay to everyone? Yeah. And that means we can take a little break before we start the homework. Today's homework, guys, I'm not going to lie, it's going to be intense. So make sure you get some carbs or some sugar into your brain during your tea break there, okay?
Is that chapter 5?
No, it's homework 5, but it's chapter 4, correct? Am I doing this right? Homework. Let's go here. It's homework. Wait a minute, I'm confused. It's, oh, you know why I said 5 and 5? Because I forgot you guys had that holiday. Remember you missed a Monday? So I should have said lecture 4, homework 4, shouldn't I have? Nuts. Class, I screwed you up today. I called it lecture 5, homework 5, but actually it's lecture 4, homework 4. Is that right? Fuck.
Yeah.
I think I screwed that up. I was basing it off yesterday's. Oh, shoot. Okay. Wait a minute. That says lecture 4. I'm confused as all hell. We had lecture 1. We had lecture 2. We had lecture 3. We had lecture 4. How am I confused, guys? What's going on?
Didn't we only have a part 1 of lecture 2 and not a part 2 of, or I guess it would be a part 1 of lecture 2.
Right. So it was lecture 1, homework 1.
Let's see.
Wait, something doesn't make sense because last week we did homework. Okay, how am I messed up here? Can someone tell me what I'm doing wrong?
Last week we did homework 3. The week before we did S1. So this is homework 4.
Then why do I have here? Oh, right.
Yeah,
Look.
we've only done 3 homeworks.
So yes, so all right. So yeah, no, it's right. Lecture 4. This is lecture 4, part 2, homework 4. Okay, I see. Wow, I just got myself all mixed up. Okay, guys, I sent out an email today saying today's lecture was lecture 5, homework 5, but that should have said lecture 4, homework 4. Do we all understand now? I'm straight, which is good. Okay. Guys, let's take a good 10 or 15 minutes to chill out and take a pause, okay? When I come back, we'll attack the homework and we'll beast it out. So I'm stopping the recording for now. Don't let me forget to start it up again. Hello, everyone. I'm back. I'm sorry I got a little distracted while reading the recaps of last night's debate. I fell into a news hole for a second, but I'm here and I'm ready to do some homework if you guys are. Joel, have you got those numbers for me?
I got the numbers, Brendan, too.
Okay. Hold on, wait, just give me 1 second. Let's, as usual, put our name on the page. Astronomy 1010, whatever your section is. Once again, I made a mistake during my morning email. This is homework number 4 that we're doing today. I apologize. I said it was going to be homework number 5 in the email. And homework number 4 is chapter 4. And okay, give me the numbers.
45.
45?
40, 47. 56. 57, A, B, and C. And
I might have us just do A and B. Let's see how far we're getting along, and then.
okay. And 58 A and C.
I may decide to remove part C's if this goes on for too long. So let's keep that as an option. I'd like us to do the part C, but if it starts taking a long time, we'll stop there. Okay, so let's start with chapter 4, number 45. Joel, you were speaking there, so just read me. What's the title in the question?
All right, the gravitational law. How does, part A, how does quadrupling the distance between two objects affect the gravitational force between them?
Okay, class. To answer these questions, we're going to be using the Newtonian version of the law of gravity. The force of gravity is proportional to the product of the two masses and inversely proportional to the square of the distance. Let's write it down like that. Part A says quadrupling the distance, which of course means the D is going to increase by a factor of 4. Let's remember how I did this during the lecture today. The force is proportional to 1 over the distance squared. What do I do now, class? Notice that I'm neglecting the masses because they're not changing.
Plug the 4 into the distance.
Nice. And what does that give us, Rory?
16.
Not 16, but be careful here.
Oh, 1 over 16?
Yeah, that's kind of an important thing, right?
Okay. Yep, my bad. My bad.
That's all right. So what's the interpretation here? How do we explain this? What does the 1/16 mean?
So it would be the new force is 1/16 the old force.
Or in other words, that's the same as saying the new force is 16 times weaker, right?
Yes.
Excuse me. Coughing on my sandwich here. All right, part B.
1 second.
Sure.
All right, so part B. Suppose the sun were somehow replaced by a star with twice as much mass. What would happen to the gravitational force between Earth and Sun?
How would I write my proportionality symbol here? Force is proportional to what? Hey, Cam, what do you think? Sure, the existing sun, the hypothetical sun, whatever you want to say, Enrique. I'm interested in what's the proportionality argument here. You guys, does anyone understand my speech here? What I'm trying to do? Rory?
Would you do, I'm sorry, I don't have the thing in front of me. Is it to both masses or is it only one of the masses?
Just to one of the masses.
So would it be, could you write like 2m1 or 2 times?
First you would neglect the things that aren't varying, and you would write force is proportional to one of the masses, right?
Yeah.
We'll substitute the 2 in next, right? One step at a time.
Okay.
So now If the mass doubles, we just plug in a 2. Right?
Okay. Okay.
So what's the answer?
Gonna be 2 times stronger.
Thank you. Okay, part C.
Suppose Earth were moved to 1/3 of its current distance from the sun. What would happen to the gravitational force between Earth and the sun?
So if I were to write this symbolically, what is the force proportional to here?
It would be 3 times greater.
Could we just do it in the same way that we did all the others?
Okay.
So distance.
Okay, so what do I write, Rory? Symbolically.
Well, would you start by just writing d squared and then
Like this?
plug it in?
1 over that.
Yeah.
Oh, okay.
You have to keep it in the bottom. It's not proportional to the distance squared. It is inversely proportional to the distance squared, and that matters. Thank you, whoever said that. Now what do I do?
One over 1/3 squared.
And what does that work out to?
1 over 1/9.
That's right, because you have to distribute the square to both the 1 and to the 3. What is 1 over 1/9?
9.
And thus, what can we say
The
about the new force?
gravitational force would be 9 times stronger.
Okay. 1 down, 4 to go. Andrew, let me know when you're good.
I'm good.
Okay, let's erase this. Jake, are you still without sound?
No, I got it back.
Could you read 47?
Sure. 47. Head to foot tides. You and Earth attract each other gravitationally, so you should also be subject to a tidal force resulting from the difference between the gravitational attraction felt by your feet and that felt by your head, at least when you are standing. Explain why you can't feel this tidal force.
All right, look, we didn't quite get to tides in today's lecture. I'm going to cover tides at the beginning of next Monday's lecture. So I can just kind of walk you through this question as best I can. We have a lot to do today, so I don't think it would hurt to make this sped up a bit. Let me explain what this question is asking. The question is not asking about the moon in any way. It's suggesting that Earth should exert a tidal force on a man just by themselves. Now, the tidal force is a differential force. And that that means something, but what does it mean? It means that the tidal force is a delta force, a change in force. It's the difference between the force exerted on a man's foot minus the difference exerted on a man's head from Earth. In other words, well, can any of you understand why there should be a difference in the gravitational force on your feet versus on your head? Why should there be two forces, one on your feet and one on your head? There's the force on your foot.
Because we have height.
Because we have height. And keep going.
Distance.
With distance.
There's,
your head is a little bit farther away than the Earth. Now, when people talk about the height of a typical average man, they often say the typical human is roughly 2 meters tall. We're clearly taller than 1 meter. I'm probably 1.6 or 1.7 meters at best. But if you just round it to one significant figure, the average human's close to 2 meters tall. The radius of the Earth, however, is greater than that. The radius of the Earth is 6,400 kilometers. How many meters would that be? Hey, Andrew, what's the conversion from meters to kilometers?
Meters to kilometers. So 1 meter is 1,000 kilometers.
Wait a minute. I'm not sure about that.
Oh, wait. I think I got it.
Yeah.
Wait, is it meters to, what is it, meters to kilometers?
Yeah,
you
said 1 meter is 1,000 kilometers. That makes me nervous.
Oh, I was thinking of kilograms. Oh, where is it? I had it.
Andrew, it should just be like one page back in your notes. What did we do the last time we did dimensional analysis together? You shouldn't have to flip back 20 pages. It should be right the page just before. Andy?
Oh, I found it. 1 kilometer is 1,000 meters.
That's right.
Yeah, I found it. All right.
Okay, so what does that turn out to be? 6.4.
That turns out.
Oh. Sorry, I accidentally wrote the whole thing down. 6.4 times 10 to the 6 meters. So class, why don't I notice a tidal force between my feet and my head?
Because it's such a minuscule.
That's right.
No.
The person's height is millions of times smaller than the radius of Earth. So the variation in force will also be very tiny. So we can write a person will not feel a tidal force because the 2 meter height of a man is millions of times smaller than the radius of Earth. Therefore, the difference in force between the Earth's gravity on your feet and the gravity on your head is essentially zero. Okay, class, take 1 second here just to pause and to write that down. Okay, so did everyone get a chance to write that down? I'll assume the answer is yes, since I gave you a little pause there. I'm going to erase, and we'll move on to the next one. I feel a little bad. That question on tides, it would have been a lot nicer if we had gotten to the discussion of tides today, but I made the choice to focus on these next questions instead. So we've knocked off 47, and now it's time for 56. Nicole, how do you feel about reading a question? You cool with that?
Yeah, just 1 second.
Yeah, take your time. Nicole?
Okay, so 56 says, find the orbital period of a planet in each. Sorry, I'm using my phone for this.
Version of Kepler's third law, right?
Yeah. And it says part A, a planet with twice Earth's mass orbiting at a distance of 1 astronomical units from a star with the same mass as the sun.
Okay. So it was a planet with twice the mass of Earth. So I'm going to write 2 Earth masses. You said the distance was 1 astronomical unit, and it was the same mass as the sun. So 1 times the mass of the sun. Okay, now in the problem, Nicole, I think you might have missed a part of the reading there, but it said these problems are so simple you will not need a calculator. That is definitely not true here, because we're using Newton's version of Kepler's third law, and we're going to want to solve for the period of this new hypothetical planet. Let's focus on the symbols. We know what 4 is, we know what pi is, and we know what g is. G is 7 times 10 to the minus 11 meters cubed per kilogram per second squared. As we talked with Rory about, that's always the same. Let's talk about the A for a second. What is the A in this case? Okay, Brooke, I'll have that recording up as soon as I can. Can someone out there tell me what the A is?
Is that the 1 AU?
Mm-hmm. But according to our lecture notes, what units are we supposed to use for Newton's version of Kepler's third law?
Has to be in meters.
That's right.
So
what do we do about that, Joel?
do a conversion.
Okay, why don't you show these guys how it's done?
So you do the division bar
Okay.
with kilometers on top,
Yep.
AU on bottom,
Okay.
then another division bar,
Yep.
and meters on top, kilometers on bottom.
Nice. Notice that Joel has carefully balanced out his units. AU cancel with AU. Kilometers cancel with kilometers. Excuse me. All right, Joel, now drop in the numbers.
150 times 10 to the 6th on top, 1
Yep.
on bottom,
Yep.
and then 1,000 over 1 on the, yeah, right there.
Okay. Nice. So if we do all that up, can you do that in your head, Joel?
150 times 10 to the 9th.
Yeah, he just took those 3 zeros and added them on here. Okay, that takes care of A for us. Now we have A as 150 billion meters. Now I'd like to focus on the masses here. While we could put the masses in, sometimes it's nice to write the total mass down first. In this case, the total mass is everything that you see in the parentheses, which is 1 times the mass of the sun plus 2 times the mass of the Earth. And I think it would be instructive if we tried to calculate that separate and then use it in the formula, okay? So watch my moves here. First thing I'll do is the mass of the sun from today's lecture is 2 times 10 to the 30 kilograms. And then we're going to multiply, or sorry, we're going to add plus 2 times the mass of the Earth from today's lecture is 6 times 10 to the 24 kilograms. Everyone go ahead and punch that into your calculators. I hope you know how to punch that into your calculators at this point. So add that up. Tell me what you get, Rory.
2 times 10 to the 30.
Units?
Kilograms.
Hold on, Rory. Isn't that just the mass of the sun? Weren't you supposed to add the mass of Earth to it?
Did I not add them? Yeah, I thought I did.
So what happened there, buddy?
I don't know. Hang on.
Huh?
So it's insignificant.
Wait, who said that?
Noah.
Where are you here, Noah? Are you real?
Yeah.
Are you a troll? Oh, there you are. Hey, Noah, I guess I can't trick you, huh? You're too clever for that. Could you explain to us once again what's going on?
Well, the mass of the sun is so massive that like adding the mass of the Earth to it isn't really going to change much.
Very good. So that's a trick, Noah, that I wanted to make sure that everyone would recognize, but it's not always obvious the first time you do this. Noah's saying, okay, this might be 2 times the mass of the Earth, but you can almost neglect, because this adds, it's like adding like 2 cents onto $2 billion. So in this case, what's the trick, and this is a trick, is that M1 plus M2, the total mass, can actually just be approximated as the mass of the sun. And that's a trick that, well, someone's got to show it to you your first time around. The total mass is basically just the mass of the sun. And that means now we're kind of ready to plug all of this stuff in, all right? Now, NK3 solves for p squared. And what I'm going to do is when I write this down, I'm going to put the square root on the other, I'm going to put the square on the other side and turn it into a square root. That way I'm just solving for the period. And here's how we're going to write this down, okay? So follow me here. This is going to be a little intense your first time around. So P is equal to the nice, big, neat square root. Make sure it's a big square root, because we're going to need to put a fraction bar inside of it. So 4 times pi squared times, I want you to watch how I write this. Now we're going to put in the A here. 150 billion meters, and that's cubed. I've got parentheses there for the units as well as the number. Divided by big G, 7 times 10 to the minus 11, and that's meters cubed per kilogram per second squared times the mass of the sun, two times 10 to the 30 kilograms. Now, we need to have a talk about how to punch this in, but let me just give you a second to catch up to me here. Okay. Let's talk about it before we do it, because this is intense, right? So we're going to do 4 times pi squared times, we don't need the parentheses, we're going to do 150 exp9, then we're going to hit the cube key. Then we're going to divide by G, 7 exp minus 11, and this is the critical step right there. When you get to this part, you're going to hit divide, not times. You're going to hit divide to let the calculator know that this is in the bottom. Then we're going to hit equals to do all of this, and then we're going to square root. All right, you ready to see it for reals? I'm going to have to stand in front of you and block this. Cam, Adam, do you have all this written down? Okay. Let me get my focus on. I think that's pretty good. Okay. Here we go. So let's do the top. So we'll do 4 times pi, hit the exp for pi, squared, times 150 exp9. Now we've got to cube it, and the cube key is, we have to hit shift first. Shift, and there's cube. Now we divide 7 exp negative 11. And here's the critical step. We're now going to divide by 2 exp 30. Then we're going to hit equals. Now we have to square root. Shift, square root. That's what you should see in your calculator. Everybody hold them up.
Let's go.
Noah, can you get yours a little closer? Bella, good. Rory, good. Jake, good. Andrew, good. Good. Noah, I like it. Noah, can I see your calculator again? Hold it up closer. Okay, yeah. You did it nicely. Okay. How should we round our answer?
Are we rounding it to just one number?
We should keep at least 2 this time. Two sig figs.
Would it be 3.2 to the 5th? I mean, sorry, times 10 to the 5th.
Small.
That's wicked wrong. Yeah.
I would do 31 times 10 to the 6th.
Yeah, Cam, you got it right. Look, before we do the 31, Joel, yes, I would do that too, but these guys are kind of, they're lost, okay? Like, if you can look at this number, but you don't know how to translate it, we shouldn't mess around with the 31. Let's just put it in simple scientific notation for now. So, Cam, can you round that to simple scientific notation for me? Three-point what? I'm scared. Cam, do you know how to do this? Let me get a pencil.
Is it 3.1 times 10 to the 7th?
Yes. Okay, yes, yes. Now, whoever got the 3.2, that was weird.
Yeah, that was my bad.
Okay, so I just want you to recognize that this 8 rounds that to 1. So it's 3.1, and the decimal point moves 1, 2, 3, 4, 5, 6, 7 places. Joel wanted to write it as 31 times 10 to the 6. That's cool too, but let's make it 3.1 times 10 to the 7. What are the units? Sorry. I'm all messed up. What's 3.1 times 10 to the 7? Units are kind of tricky here.
Seconds.
Yeah, so let's look at what happens. Meters cubed cancels with meters cubed. Kilograms cancels with kilograms. 1 divided by 1 over seconds squared is seconds squared. And then the square root of seconds squared is just seconds. That's our answer. But for completeness, we should convert the answer to years. I'm going to ask a special victim to do this for me. And the special victim is Adam. Adam, you're my special victim today, okay? Adam, we have our answer. It's 3.1 times 10 to the 7 seconds. But what I need from you, if you got the time, I need you to help me convert that to years using dimensional analysis, okay? There's no sense in hiding from it. You're gonna have to do it in the exam.
Okay.
Okay, here's how you're gonna do this. Do you have your 4 steps of dimensional analysis from the first lecture? Can you find those in your notes? So flip your notebook all the way back to the first day and look for the thing with 3 stars next to it that should say the 4 steps of dimensional analysis.
So first step is write down the number to convert with its units.
So what do I write down?
So you would write down 3.1 times 7 or times 10 to the 7th seconds.
Good. What's the second step?
Second step is multiply by a division bar.
Third step.
Put units in first to connect.
Cancel. To cancel.
I can't
All right,
tell.
so what unit should go on the bottom and what should go on the top?
So seconds would go on the bottom,
Correct.
and then you would put years on the top.
Now, Adam, that is an okay maneuver. You could do that, but Adam, you can only do that. Step 4 says use conversion factors to put the numbers in. So Adam, you can only do this if you know the conversion factor between seconds and a year. So I'm asking you personally, do you know how many seconds are in a year?
Not off the top.
I didn't think so. In that case, Adam, you're going to need a better strategy. You're not going to be able to go directly from seconds to years. You're going to have to leapfrog. Do you know the number of seconds in some other unit of time?
A minute.
Okay, so let's put minutes on the top instead. Now seconds cancel and you're converting to minutes. Now, do you want to put the numbers in next? That's step 4. How many minutes and how many seconds?
So 60 minutes or 1 minute.
Yep.
And 60 seconds.
Good. Okay, so you've now converted to minutes. Now we're going to have to go back to step 2. We're going to make another division bar. Now go to step 3. What's step 3?
So put in the units. So put minutes on the bottom, and then hour on the top.
Okay, and what's my conversion factor there?
1 hour is 60 minutes.
Okay, let's go back. Now minutes have canceled. What are my next set of units?
It would be hours to days. So you'd put day on top and then hour on the bottom.
And how many hours in a day?
24.
So 1 day is 24 hours. And lastly, now you can go to years, because I'm guessing, I bet you know the number of days in a year, right?
Right. 360.
Sorry, I missed what you said.
Oh, 365.
Yeah. So 1 year is 365 days. And that's how we convert to years. Okay, now punch them up. Take that number, divide by 60, divide by 60, divide by 24, divide by 365. They're all on the bottom, so you have to divide multiple times. And what do you get? Well,
I got 0.9830.
this is really close to what number? Wicked close to?
To 1.0.
Just 1. 1 year. And you know what you should write next to that? You should write, duh. Of course it's 1 year, guys. You have a planet orbiting the sun at 1 AU. Any planet which orbits the same sun at the same distance will have the same period as Earth. Sure, the planet is twice as massive, but it doesn't matter because Noah proved to us that the mass of the planet is insignificant compared to the mass of the sun. In that case, p squared equals a cubed holds. And 1 AU will give you a period of 1 year. Well, we learned something in any case. Now let's move on to part B. Does everyone have this written down? Because I need to erase.
I'm all set.
Okay. I'm erasing. Okay, what was part B again? Who was our reader there? Was that you, Adam? I can't remember who was reading. But who was reading?
It's Nicole. So
that's right,
part
Nicole.
B is a planet with Earth's mass orbiting at a distance of 1 astronomical units from a star with 4 times the sun's mass.
This is a different scenario here because now the planet is the same as Earth, but the mass of the star is different. If it's 1 AU, our A is still the same. Our A is still 150 billion meters. That's easy enough. Hey, Noah, you're such a hot shot. So what would the total mass be here? If it's 4 times the mass of the sun plus 1 times the mass of the Earth, how would you simplify that?
4 times the mass of the sun?
Yeah. In other words, you were a little quiet there, but I think what you said was we still neglect the mass of the planet, but we cannot neglect the mass of the star, so it's going to be 4 times the mass of the sun. So let's go ahead and solve that now. P is equal to the nice big square root of 4 times pi squared times 150 billion meters cubed divided by G, 7 times 10 to the minus 11 meters cubed per kilogram per second squared, times 4 times the mass of the sun. Now, during our last example, I taught you guys how to punch this, but I need to get you guys to a point where you can punch this without me. So I'm guessing about half of you at least will get this wrong, but it will be a useful exercise, not a useless exercise. It'll be a useful exercise if you guys could try this first. Let's see what fraction of you gets it right, what fraction of you gets it wrong, and then I'll walk you through if a high number of you are getting it wrong. I'll walk you through even if one of you is getting it wrong. But I want you to try first. So get me something. I'll stay out of the way here so I don't block your calculator, your thing. And get me a number and then hold it up so I can see what's going on. Rory, I'm afraid that's incorrect. Let's see if any of you can get it. Joel has it. Bella, Bella, that's, you need to square root, Bella. You forgot to square root. Jake, I'm afraid that's not right. Sorry, Jake. Bella, you almost had it. You just needed to square root. There you go. So far, Bella and Joel have it. Rory and Jake, I think, are having a little trouble. Yin, what are you getting? How about you trolls? What are the trolls up to? Hold on. Let me go to speaker view. Doesn't look good, Rory.
I'm just lost.
All right. Okay. All right. Let's do this together. Hey, Cam got it. Cam. Smooth moves, buddy. Smooth moves. And Adam, no. Adam, you forgot to hit divide on the bottom. I can tell what you did. All right. Look, let's just do this together here. Let me go to my speaker view. Let me adjust the focus here. Okay. Y'all ready? Y'all better watch this here because many of you goofed. I'm trying to hold this in such a way that all right. 4 times pi squared times 150 exp9 shift cube divide by 7 exp negative 11 divide by 4 divide by 2 exp30 equals shift square root. Hold them up. Let me see what we got. Yin, yes. Rory, yes. Jake, yes. Andrew, yes. Adam, what's shaking with your bacon?
I did cubed instead of squared. So I'm just redoing it.
Wait, you were supposed to hit cube, right? You're supposed, wait, I don't, there are two different parts you could be talking about, Adam. When you're here, you should definitely hit cubed. When you're
The very last step.
Oh, that should be square root, right? So you got to do shift square root. All right. What should I round my answer to, class?
One point times 10 to the 7th.
1 point what?
5.
What are the units? Units, Rory?
Seconds.
Rory, if I was to give you a big hint.
Yeah.
Rory, if I was to tell you that 1 year is equal to 3.15 times 10 to the 7 seconds. If I was to give you a big hint that I didn't give Adam, would you be able to convert that to years for me real quick?
Ooh.
I made Adam do it the hard way, but I'm gonna let you do it the shortcut way. How would you do that, Rory?
I
I want to know how many years this is.
I got confused, yeah.
Why don't we use the 4 steps of dimensional analysis?
Okay.
What's your first step?
So times the division bar.
No, your first step is to write down the number you want to convert with its units.
Oh, yeah, sorry, I already have it written down.
The second step is your division bar.
Yeah.
What's my third step?
And then you can do the units. Are we doing it the long way, or?
Well, you can do it any way you want, but I just gave you a big fucking hint there.
Yeah, I know you did. It's okay. So is it 3? So it's
wait,
30.
Units first, Rory. Units first.
Okay. So seconds on the bottom, and years on the top.
Okay.
And then it would be 31,500,000.
Just scientific notation is fine.
3.15 times 10 to the 7 on the bottom.
What goes on the top?
1 year.
Boy, if only Adam had had that, that would have made his job easier. Okay, punch him up. Tell me how many years you got. That's a little tiny. I'm going to try to write that bigger. Noah, you're off a little bit. Could you just tell me the answer?
Whoa.
Is it 0.48?
Or round it harder.
0.5? Is that where you're going at?
Yeah.
Oh, okay.
0.5 years. Or half a year. So a star with 4 times the mass of the sun would change the period by half. I want to show you guys a little secret. We could have done this problem a whole lot faster if we had had the power of proportionality arguments on our side. If we were to write NK3 as a proportionality argument, we could write P squared is proportional to A cubed over the total mass of the system. When I use proportionalities, I can neglect the constants like 4s and pi's and g's. Now in this case, we had a distance that was 1 AU, but the mass was 4 times that of the sun. And that means basically P squared is proportional to 1 cubed over 4, which implies that P is proportional to the square root of 1/4, or P is proportional to half. So that if I quadruple the mass, the period would drop by half. We could have done that in 2 lines without a calculator, only if we understood how to use those proportionality arguments. You guys, unfortunately, do not know how to do that. You weren't ready for that. So I had to make you do it the hard way. But wouldn't it be cool if you learned how to do that? Then you could do these problems much faster. The moral of the story is that proportionality arguments are useful. All right, 3 down, 2 to go. Let's try 57 now. Andrew, can I erase?
Yeah.
All right. $57. Noah, can you read that?
I actually don't have it out in front of me.
Well, geez, what are you? You just middle managing there or something? Who does? I don't remember who's read and who. Rory, did you read yet?
I haven't. I got you.
Okay.
Let me find it.
I give you the questions right in a little homework session, right? Of Blackboard.
Am I just reading A?
Read me the title, read me
And,
everything,
like, the
and then
first part.
stop at A, yeah.
Okay. Using Newton's version of Kepler's third law, calculate Earth's approximate mass from the fact that the moon orbits Earth every 27.3 days at an average distance of 384,000 kilometers.
Okay, the moon has a period of 27.3 days and a distance of 384,000 kilometers. In this problem, we're going to be doing things a little bit differently than we did in the last time. The first time you learned NK3, you learned it in this version. P squared is 4 pi squared A cubed over G times the sum of the masses. Here, I'm going to solve for the sum of the masses by taking m1 plus m2 and flipping them up to the top and taking p squared and putting it on the bottom. And I then get a new formula called NK3, but solved for mass. And it goes that the total mass of the system, that is the sum of m1 plus m2, is equal to 4 times pi times a cubed over g times p squared. This is the version of the formula that we're going to use for A and B. And honestly, guys, because I knew this lab would take, this lecture would take a while, we're going to just do 57A and B, and we're going to do 58A. That's going to be enough for us. Go ahead and put a box around this because it's kind of a big deal. Please remember that these formulas require Mks units. So what am I going to have to do, Rory, before I can start the problem here?
You're going to have to convert days to seconds.
And?
Kilometers to meters.
That's right.
Sorry, I lagged for a second.
You had what?
I lagged out for a second. My computer froze. So.
Okay, Rory, just to try to speed things up, you and I just did a dimensional analysis together, and you seem to kind of know what you're doing there.
Yeah.
So, you know, it's fun to torture other people, but why don't you help me with the days to second bit? Because I think you've got this now.
Okay, so it would be.
What do I do? How do I go about it?
Okay. So write down your number you want to convert.
With its units.
Yeah, with the units. And then multiply by the division bar. And then units, so days on the bottom. And we're going to seconds. So second, can we just do seconds on top?
Do you know how many seconds are in a day? No, you don't. So why don't you put another unit?
Seconds in a minute. Okay. So hours?
Yes.
Oh.
Let's put all the units in first. That takes care of days. Then what?
Okay. And then the next one, you're going to do hours on bottom and minutes on top.
That takes care of hours. And then?
Minutes on bottom, seconds on top.
All right. So basically, Rory, we did all of our step 3 at once, which is a cool way to do it. And now give me all the numbers.
All right. So 1 day and 24 hours.
Where does the 1 and where does the 24 go? I want you to be very explicit with me.
1 on the bottom, 24 on top.
Okay. Keep going.
1 on the bottom, 60 on top. And 1 on the bottom, 60 on top.
Excellent. Okay, now punch that into your calculators and tell me how many seconds you got. 3 sig figs works. I think I'm allergic to math. Whew. I took some melatonin to sleep last night, and man, am I really groggy today. Not my best day to be groggy.
That's supposed to take the whole bottom.
No, I take half. It's like a 3 milligram chewable from Trader Joe's, and I bite it in half. But that stuff is so powerful for me. It really knocks me the heck out.
That looks good, Andrew.
Oh, what'd you get, Andy?
23%.
No. Do I have to do this? If I have to do this, then you're all fired. Can I see? Cam, oh.
He's just reading it wrong, Brendan.
Oh. Can you read it right? That's kind of part of it. How do I do that?
Oh, me?
Yeah.
Yeah.
All right. So you're gonna do 27.3.
Well, just reread your answer, Andrew. You read it wrong.
Oh.
Andrew, is your number bigger than 1 million or less than 1 million?
Bigger than 1 million by.
Then you should put it in scientific notation. That's the
All
rule
right.
we all agreed to.
So it'd be 23.
How about 2.4?
All right. 2.4 times 10 to the 6.
And the units?
Years.
Nope.
Or
Look
no
at your
way.
dimensional analysis. What units are left over, Andrew?
Oh, seconds.
Yeah. Remember, if it's bigger than 1 million, put it right into dimensional. Hey, Cam. Cam, you're up. Help me convert 384,000 kilometers into meters. I can't hear you, Cam. Cam, can you unmute yourself just so I know that we're talking here? Because this pause is kind of awkward for me. Hi. Cam, are you there? I can't hear you, homie. I see that you're unmuted, but can you just say hi to me? Do you have no microphone? Oh, you had your headset, but your headset is missing? Oh, balls. Oh, so, I'm sorry, I shouldn't say that. Okay, look. Okay, Cam, you're useless. Noah, can you help me, please?
Yeah, what do you need?
Convert 384,000 kilometers to meters. I need to make sure that you guys can do this, you know?
So you start off with 384,000 kilometers.
1,000 kilometers, yep.
Then you multiply by a division bar. And you're gonna put meters on top, kilometers on the bottom.
Thank you. And now?
1,000 on top and 1 on the bottom.
Beautiful. Can you do that in your head, Noah? Because you're so good.
Yeah. Do you want me to put it in scientific notation or?
Yeah, but you can leave it. You can leave your lead digit as 384 if you like.
Right. So 384 times 10 to the 6th.
Yeah, that's the easiest way to write it. And that's meters. Okay, thanks, dude. Now we're ready to plug into our equation. Now remember, the total mass. Wait, Noah, I still need your help. The total mass is the mass of the Earth plus the mass of the moon. Would you say I could make any simplifying approximations here, Noah?
I don't think it's that small that you could do that.
It turns out there's a hint in the problem. And what does the hint say? Who is reading? Rory? What's the hint say?
I was. Hang on, I gotta pull it up. Calculate Earth's approximate mass and the fact that moons. I don't know what the hint is that I'm trying to find here. Calculate Earth's approximate mass from the fact that moon orbits every 27.3 days.
I thought. Maybe they've changed it in this edition, but chapter 4. What number was this? 57?
Yes.
Oh, wow. Back in the day, they used to give you a hint there. So, hey, Noah, what if I give you the hint instead? Noah, what if I were to tell you that the mass of the moon is, approximately speaking, 1/80th of the mass of the Earth? Is that something we can deal with, or?
I mean,
Let's look at an 80th here. 1 divided by 80. If you're just thinking about size, that's a hundredth.
yeah, okay, then that's probably insignificant.
Yeah, it's a penny out of a dollar, right? But I could see getting jittery about 1/100th. Noah, the reason why you got bamboozled there is kind of interesting. The moon is 1/3 the size of Earth, which would certainly be significant if it was mass. But even though it's 1/3 the size, you're going to learn a little bit about the interior of the moon in an upcoming lecture. We're going to talk about planetary science a bit. It turns out that the moon is weirdly devoid of metal in its core. So whereas Earth has a molten nickel iron core, which is very, very dense, the moon is kind of weird in that it does not have much of a metal core at all. It's mostly just a lump of rock. And because of that, even though it's kind of 1/3 the size, it's only an 80th or 100th of the mass of Earth. So, 99 cents versus $1 is more or less the same thing. So I think we can neglect the mass of the moon here. I'd say you only start to have to get jittery when it's like 1/10 or 1/20th. That's when you have to start thinking about it, okay? So we're going to neglect the mass of the moon, and we're going to say it's approximately the mass of the Earth. And now we're going to plug in all of our values. We're going to have 4 times pi squared times 384 million meters cubed divided by big G, 7 times 10 to the minus 11 meters cubed per kilogram per second squared. Sorry, trying to make that neat. Times, open parentheses, 2.4 million seconds squared. Okay, once again, before I show you how to punch it in, do your best shot and see if you can get something from me. Let's see what fraction of you can get it right. I'm hoping that number is going to start going up. Okay, what you got for me? Joel, doesn't work.
Do we have to root it?
Yes, Rory. Wait, ruin it?
Oh,
Wait, what was the question? I don't understand. Rory, you got it.
yeah, she asked if we root it, square root it.
No, no. It does not say. We don't need to square root it here because that's now bound up in the square. You've got to square this beast. Jake, you're off. I don't know what you did there, but I think you forgot to cube, Jake. Yes, Cam. Cam, you're slaying it. Bella's got it. Cam and Bella and Rory have it. Noah, let me just.
Oh, damn it.
Oh, you got
I
it.
did forget to cube it.
Yes, Zach. Zach has it. Smooth moves, buddy.
Oh, wait.
Oh, can you hear me, by the way? I found my headphones.
Oh, you found your headset. Killer Cam. Thanks. Okay, we'll need your help.
All right.
You might want to turn your mic up a teensy bit since you're You're a little soft spoken.
Okay.
That better, Brennan?
Something's still wrong, Joel.
Wait, do you put in the parentheses?
Oh,
You might have forgotten to square. Oh no, Adam,
I
I know.
didn't square the pi.
Adam, I'll show you what you did, Adam. Right down here. Do you see this? You can't hit times there, Adam. You have to hit divide. That's what you're doing wrong, okay? Try it again. Keep doing it until you get it.
I have a question.
Do I have to use parentheses?
No, you don't, because the EXP takes care of that. Yeah, Jake, what's your question?
So once you get to the last part, like, and you typing it in 2.4 exp6.
Yep.
And then you square that.
And then you hit equals.
And then you hit equals. And then you square it again.
Now you got it, Joel. No, then you do nothing.
I mean, square root it.
No, you don't need to square root it. There is no square root this time.
Oh, yeah, I'm just like so far gone. Okay, I got it.
All right, I think it's time for me to do it. Ready? I'm going to move quick, so keep up with me here. This is for the night class too, all right? 4 times pi squared times...
Wait, what?
Yep. Sorry. You want me to do that again?
Yeah, you want it too fast. 4 times
exp squared times 384 exp6. Now I'm going to cube that beast by doing shift and cube. Now I'm going to divide by g, divide by 7 exp negative 11. Then I'm going to divide by 2.4 exp6. I got to square that right up here. And then equals. All right. So what do I round my answer to? Give me 2 sig figs.
5.5 times 10 to the 24th.
Units?
Seconds. Oh, wait. Are we we're finding the mass?
Yeah.
Oh.
Hey, Rory, let's
yes.
cancel out some let's do dimensional analysis.
Oh, okay.
I've got a meters cubed on the top.
Yep. Oh, 1 second.
What about the bottom?
So yeah, you have the meters cubed on the bottom.
So we can cancel those out.
Yeah.
What else do you have?
I think isn't that because there's no seconds on top.
Well, there's seconds on the top of the bottom, and there's seconds on the bottom of the bottom. In fact, there's seconds squared on both.
Oh, okay. So do those cancel out, or would you put those?
Yeah.
Oh, okay.
Top of the top and the bottom of the top of the bottom and the bottom of the bottom. So what do you have left?
Kilograms.
Yeah, 1 over kilograms, which is also kilograms.
So if you're dividing at the bottom to show you're at the bottom, why is it a multiplication sign instead of a division sign?
Wrong, okay? I'm multiplying this fraction by that number. So Rory, what's going on there is I have 1 over seconds squared times seconds squared.
Okay.
Remember, this guy is part of a secret fraction, seconds over 1.
Yeah, I got you now. Okay.
You're getting confused because that's on the bottom of the bottom, and this looks like it's on the middle, but it's actually at the top of the bottom.
Okay.
All right,
cool.
That's an important lesson. Okay, let's erase and go to B. Rory, were you the reader just now?
I was, yes.
Okay, so I'm going to erase this, kids. Andrew, you cool?
Yeah, I'm cool.
All right.
Okay.
What does B say?
Calculate Jupiter's approximate mass from the fact that its moon, Io, orbits every 42.5 hours at an average distance of 422,000 kilometers.
Okay, let's see if we can speed this one up a little bit. So let's convert to MKS. Hey, Cam.
What's up?
42.5 hours. What do you want to convert it to?
2 seconds.
Good. Show me how to do it.
So I believe I gotta write.
Tell me what to write down.
Oh, put down 42.5 hours.
Yes.
Times, and then you'll have, yep. So at the bottom, you'll have, let me see. At the bottom, you'll have hours, and above, I think you have minutes.
Okay. Then what do I do?
Then you multiply again. And at the bottom, you'll have minutes, and at the top, you'll have seconds.
Man, you guys are getting good. Pretty soon I'll be ready to have an intelligent conversation with you. I like this. Okay, now what do I do?
As then, I guess you crossed out minutes?
Sure.
Crossed out minutes and hours.
Now you got to put in your numbers, buddy.
All right. So let me see. So,
Note from everyday life.
okay, so if there's 60 minutes an hour, so it's 60 above and 1 at the bottom. And then and for seconds you put 60, and for minutes you put 1.
Okay, punch them up. Get me my seconds.
All right.
Punch them up.
42.5.
Anyone who wants can shout out the answer. If you're fast, just shout it out.
153,000
Awesome. 153,000 seconds.
seconds. Yep.
Okay, let's do the 422,000 kilometers now. 422,000 kilometers. What's my conversion factor from kilometers to meters?
1,000 meters to 1 kilometer.
Okay. So what does that give me for meters then?
422 times 10 to the 6 meters.
Good. 422 million meters. All right, let's plug that in. The mass of Io plus the mass of Jupiter is just the mass of Jupiter. The mass of Io certainly will not add anything to Jupiter's prodigious mass. So the mass of Jupiter is basically equal to 4 times pi squared times 422 million meters cubed divided by big G, 7 times 10 to the minus 11 meters cubed per kilogram per second squared times 153,000 seconds. Squared. Okay, students, punch them up. This is a little workout for your brain. You're getting better. Anyone who thinks to get the answer should shout them out. Looks good, Jake. How do I say that? What should I write down?
1.8 times 10 to the 7th.
Wait, 7?
No, 6.
Wait, is it 7?
No, 6.
27.
Oh.
Dude, hold up your calculator again. Hold that up to me.
Oh, I'm seeing it now. I thought we were moving the
27 in the corner?
Yeah.
I thought we were moving the decimal point.
No. That means it's in scientific notation, if you see that there. So 1.8 times 10 to the 27. What are the units, Jake?
Kilograms?
Yep, looks good, Cam. Digging it. By the way, that's B. Okay. Let me know when you're ready to move on, students. One last, Noah, did you get, oh, I see. Okay. I'm going to erase now. Noah, you ready to read the problem for me or what?
Me?
Yeah, can you do that?
Yeah, let me pull it up.
While he's pulling it up, let me give you guys a little preamble. Question number 58, part A is all we're going to do, has to do with a new formula called escape velocity, okay? Let's all draw the picture of what's happening here. Where's that GD Frisbee? Oh, there it is. Okay, so we have a planet. And the planet has a radius r and a mass m. And we're trying to calculate the escape velocity. The escape velocity is how fast does your rocket need to travel to leave the gravity of the planet? And usually we call the escape velocity V subscript ESC for V escape. It turns out the escape velocity that you need to leave a planet only depends upon the planet itself. What is its mass and what is its radius? And the formula looks like this. The escape velocity is 2 times big G times the mass of the planet divided by the radius of the planet. I'll tell you a little more about this in our Monday lecture, but for now we're going to test it out. What does it ask us to do, Noah?
So it says, calculate the escape velocity from each of the following using data as needed from Appendix E. A is the surface of Mars.
Okay, and that's all we're going to do today, just as a kind of warm-up. I'll give you the data from Appendix E out of my brain. The mass of Mars is, I believe it's 6 times 10 to the 23 kilograms. It's basically 10 times less than Earth. And the radius of Mars is 3,400 kilometers. Can you guys now convert that to meters in your head? Are you that good? If you can't, then I'm going to have to make you do dimensional analysis, but I'm going to give you a fighting chance here. How many meters would that be?
400,000 or 3.4 times 10 to the 6th.
3.4 million meters. Very good. I'll let you skip that step because you've impressed me. Okay. Let's just go ahead and calculate the escape velocity. The escape velocity will be the square root of 2 times 7 times 10 to the minus 11 meters cubed per kilogram per second squared, okay, times the mass of Mars, six times 10 to the 23 kilograms, divided by the radius in meters, 3.4 million meters. I did that a little quick, but that's okay. And let's just see if you guys have the chops to punch that in. Type, unless you're Noah, type everything in, hit equals, and then square root. Noah, you can put the square root in the beginning because of your calculator.
Brendan.
Did you forget to square root it?
No. I don't think I did.
Something don't look right to me. Bella, get closer. Oh, I'm sorry. I couldn't see your decimal points. That's good. Joel, I think you had it right, but I didn't see your decimal point. Bella, yes. Cam, no.
Oh.
Joel, can I see yours again?
Let me try that one again.
I'm redoing it because you told me I was wrong.
Well, I might have lied. Jake, that doesn't look good. Did you square root it?
I did. Oh.
All right, then you
Yeah.
got to punch again. No, Rory. Yes, Joel. Yes, Noah.
Do you have to hit equals before doing the square root at the end?
Yes, that's very important. Why don't we do this one more time for the people in the back, okay?
Oh, wait.
2 times 7 exp negative 11 times 6 exp 23 divided by 3.4 exp6, then equals, then shift square root. Adam, show me what you had.
Oh, I see what I did wrong.
Okay. Adam, you were about to show me, I thought, but
I think I got it.
yeah, no. Try it again, Andrew.
I forgot to hit shift and then square root.
Yes, Rory.
Two times 7.
Wow, I gotta comb my hair.
I got it.
You got it?
That looks good.
Yeah, I got it.
That looks good, Cam.
Yep.
Thank you.
Andrew?
Yeah, I forgot to hit shift and square
Good,
root.
Jake. Good. Andrew, what's going on with you?
I'm just dividing 3.4.
Make sure you hit equals and then shift square root. Ouch. Ouch. Okay, how should I round this? 1 sig fig, Rory.
I got it. 49.
Yeah, but how do you round that, Andrew?
All right.
Round it
So
to
it's gonna
one
be-
significant figure.
Oh, it's going to go up 1. So it's going to be 50.
Not 50. That number is not 50.
5.
Um,
5,000.
5,000.
Oh.
Would you
I
agree?
just looked at the two numbers.
Nice
Andrew-
round number.
Andrew, would you agree that 50 is not the same thing as 5,000?
Yeah, I agree with that.
If I have, I just made this up, but if I have 4,879.235 to one significant figure, that's close to 5,000, right?
Yeah.
What are the units?
Wait.
What are the units?
Meters per second per second.
That's units
Oh,
of
per second. Is it seconds? Yeah. Because the other one's crossed out.
What are the units?
Seconds.
False. Seconds are a unit of time.
Kilograms?
False. Kilograms are a
Meters
unit
per
of time.
second.
No one knows. It's meters per second.
Oh.
Hey, Noah. It's customary to convert escape velocities into kilometers per second. How many kilometers per second would that be?
5.
Good. Or 5 clicks per second.
Now you're talking my language.
Yeah.
5 clicks.
I thought the military folks out there would enjoy that one. 5 clicks per second. Okay. I can't believe I did that by 2:58. Let's have a pep talk here for a second. I know for some of you that was a bit of a challenge. That's the idea. You will get stronger. You will get better. We got it done in 2 hours, which is a damn miracle, okay? Please turn that in right away and make sure your format is good. We will continue to get stronger. Now, I think there's going to be an exam coming up, not next week, but maybe the week after that. What are we looking at?
Isn't it midterms?
Yeah, when are they, Bella?
I think around like October 16th. And so,
It says October 19th.
okay. No, because I have another class and then just the schedule she put a few days earlier for hers.
Yeah, I always do mine as late as possible. One of the reasons I do mine as late as possible is you guys will get stronger with each homework we do. So each homework will give you a better chance. So we have, today's the 30th. We're kind of on track. Next week we'll do atoms and light. And then we've got an extra makeup day, which we're probably going to desperately need. And then, so, all right, we're 2 weeks away. But I just wanted to keep track of that. Guys, you're getting stronger every homework, okay? So turn those in. Do you have any questions for me?
Did I submit lab 3?
Yeah, by the way,
I'm not sure if I did or not.
a whole bunch of you are not submitting stuff, and it's really scaring the willies out of me. Cam, what section are you in? What's your last name, Cam?
Simas, S-I-M-A-S.
I have all homeworks from you, and I have all labs from you, so you're good. You're not one of them. But there are other people out there that are worrying me. I don't know if it's any of you. You guys are usually... Ava? Oh, Ava, we have to update your... Ava, it's your lab 3. Okay. Ava? Yeah, because you did something goofy. I can't remember what it was. You like uploaded the wrong... You uploaded a weird format. So Ava, I want you to see this right here. There you are, Ava. I'm putting in a 10 for you because you emailed that to me, okay? So you're good. I'll have to try to update the Blackboard at some point. That's going to be more difficult. I could try it real quick. Grade, center. I don't know if I can manually change this. It's not that easy. And Blackboard really sucks trying to find people. Ava something tobal. Where are you? Ava, oh, there you are. I just saw you for a second. Okay, Hamo. Oh, this thing is so horrible. Oh, there you are. Ah. Okay, Ava. You are legit. Anyone else have an issue? Okay. Oh yeah, the P list. Don't submit me no more P list, Ava. Make sure you give me a .jpeg or a .doc, okay? Okay. So everyone, I'm going to stop the recording. Let me stop that, and then I will say goodbye to you all.